Welcome, everyone. We're just going to wait a couple minutes so folks can join. All right, it seems like we've reached the steady state. Welcome, everyone, to the RC Fluxes from Space webinar series. It's my pleasure today to host Dan Whitt from NASA Ames, who's going to talk about some submesoscale and mesoscale processes near the Pacific Cold Tongue. Take it away, Dan.
Okay, thanks, Bia. Hi, everyone. Thanks for the opportunity to present here. So this work is going to be the presentation is going to be about super preliminary work. It's based on recent proposal that got funded from the SWAT science team. And so yeah, it's taken in that spirit. Nothing is super well developed and published. I'm looking for collaborators, and I'll just kind of try to give you an overview of some of the things I'm thinking about in this space and maybe get you excited about the general topic. Okay, so to start out, the Equatorial Pacific Cold Tongue, why focus on that? That's because it's a region of leading significance for global climate dynamics and prediction. Right, it's the plot on the left is a map of the time mean surface heat flux. The cold tongue is a hot spot of probably the most important hotspot of net heat uptake into the ocean. It's also a key hotspot of carbon outgassing. It's the center of action of El Nino, the Southern Oscillation. It's key to seasonal to interannual predictability. You also have a problem with the climate models in this region. Cold tongue biases persist in many models, for example, CESM2 and many others. So it's a region that's important for climate dynamics. And, there's a long history of study as a result because of these motivations, but the focus of the work tends to minimize the role of small-scale processes, focusing on the regional to global dynamics. And that's not to say that there's nothing going on at small scales. There's quite a lot. And I guess the question is, how do those small-scale processes participate in the large-scale dynamics? And this is just a map highlighting some of the small-scale variability in a high-resolution regional model that our group did as part of some NOAA-funded work a few years ago. And it's 5-kilometer resolution showing SST. You can see not only these sort of well-studied tropical instability waves and vortices on the northern flank of the cold tongue, but also sort of a lot of some mesoscale structure around the whole cold tongue there. And that's really highlighted more so if you take gradients. So if you look at vertical vorticity, you can see, not only the anticyclones, the tropical instability vortices there, but also all this soup of structure at sort of 10 to 100 kilometer scale around the flanks of the cold tongue. Not so much right on the equator here, but around the flanks of the cold tongue, there's a lot of structure, which really hasn't been very much studied. There's the Coriolis frequency for reference. And I'm blocking my own screen, but you can get a sense of the Rossby numbers right away. So the vorticity, in the color bar divided by the Coriolis frequency is of order 1. Okay. And so some high resolution climate models have shown mesoscale and some mesoscale processes are important for large scales. And certainly, there's some studies about the role of the tropical instability waves, but the sort of role of this smaller scale structure remains somewhat unclear. And I mean, a problem is that typical climate models don't resolve these structures. So getting the scale interactions is challenging. And even ultra high resolution state-of-the-art ocean models have difficulties with tropical surface currents. And this is a nice plot I like from one of Brian Arbick's recent papers. This is a zonal around the entire globe, not just this one region, but it's showing a comparison between undrogued on the top surface drifters measured of kinetic energy, and on the lower plot drogued 15-meter. These are these standard global drifter program drifters and HICOM and MIT GCM at high resolution configurations, nominal 1/48th and 1/25th of a degree. And you can see that there's quite a discrepancy, and this is 2-day period and longer, so quote low frequency in their terminology, kinetic energy. And so there's quite a discrepancy in the equatorial band between the observations and the models. And these are comparisons between Eulerian measures in the models and Lagrangian measures so there's some potential for discrepancy there, but it looks like from some of the work that I've seen, this is not causing the discrepancy here. It's really a physical thing, not just a difference in reference frame. Okay. And, a further complication here is that this region, it's difficult to measure surface currents. So, one of the main global array for measuring surface currents at the moment is the Global Drifter Program. This is a just randomly selected map of drifter locations, gray without drogues and magenta with drogues. And because of the equatorial surface divergence, it's challenging to maintain the density of the drifters in the region of interest here. And so you can see they pile up in the subtropical gyres, but you tend to not have as many drifters in the equatorial region. So that makes it difficult to measure these features. And I guess what I'm trying to argue overall is that improved observations and parameterizations of sub-mesoscale surface currents, mesoscale and sub-mesoscale really, in the cold tongue may be critical for improving models and making predictions of global climate. And it's an unproven thing, but that's what I'm working towards, or the premise I'm considering. And so, okay, so what am I want to step back here a little bit and talk about sub-mesoscale. Sub-mesoscale currents have been extensively studied in the last 20 years. Observationally, models led the way 20 years ago, but the observations have been intensive and extensive really over the last 20 years. But most of the attention is focused on the mid-latitudes. And this is, here's several review papers, right? I'm taking a figure from this one by John Taylor and Andy Thompson just last year, and they're characterizing, how sub-mesoscales relate to mesoscales and three-dimensional boundary layer turbulence, for example, in terms of aspect ratio on the y-axis and Rossby number on the x-axis. And some mesoscales occupy this space of order 1 Rossby number here. And the contours are telling you about the vertical velocity. And a characteristic, so I'm just listing some features. So features we typically define some mesoscales as dynamically based on the Rossby number, Froude number, Richardson number, which is not explicitly here. And length scales are typically 100 meters to 10 kilometers, and aspect ratios are maybe 1/100. So the equatorial zone, things are going to be in some ways similar, in some ways different. So first of all, I'm claiming that the models reveal some mesoscale currents around the equatorial Pacific cold tongue, but what exactly do I mean by that? And the first thing I'm going to say is I'm going to define it in these ways: these dynamical sense, Rossby number, Froude number. But you're going to see that the aspect ratios and length scales are a little bit different than what you typically see at mid-latitudes, and that has implications. So you can see from this plot here that the Rossby number of, say, these vortical structures and frontal structures on the northern flank of the cold tongue is of order 1. There's F there. If you look at a section through that magenta line in the vertical in a model, right? It's the same model we were looking at. You can see meridional velocities of, order 0.5 meter per second. Lots of structure here. The mixed layer depth is a magenta moving up and down. The vertical vorticity here is now normalized by F, so you can actually see the Rossby numbers of order 1 there, especially in the smaller scale structures. The Froude number was the vertical shear divided by the stratification is shown here. So it's from 0 to 2 range. You can see that a lot of the structure in the boundary layer has Froude number of order 1. And then you have vertical velocities down here in meters per day. And I want to emphasize, so a lot of the focus on some mesoscales at mid-latitudes derives from the fact that some mesoscales have these strong vertical velocities. So in this situation, the aspect ratios are lower, and so the vertical velocities are not as strong for characteristic Rossby and Froude or Richardson numbers of order 1. And so that's what I'm talking about when I'm talking about these motions, and I want to understand their dynamics better. And so I mentioned this new project. It's basically focused on understanding and measuring mesoscale and some mesoscale currents around the cold tongue using SWOT observations along with Lagrangian drifters and high resolution models to understand and fill in the gaps. One of the motivations is the fact that we had a strong 2023-2024 El Nino and then a transition. So SWOT is incidentally observing an interesting modulation from the perspective of large-scale tropical Pacific dynamics. We want to understand how that plays a role as well as the seasonal cycle in modulating these structures. Okay, so I'm going to talk a little bit about like the 3 parts here. One is the Lagrangian drifters. Number 2 is the SWOT observations of SSH. And number 3 is the high resolution models. And it's just going to be a quick kind of teaser. So the Lagrangian drifter releases, so this project will involve a series of Lagrangian drifter releases from Palmyra Atoll, which is at 6 north, 162 west. It's in a U.S. Territory in the Line Islands. We're going to do monthly deployments, roughly speaking, of about 5 GDP. This is the Global Drifter Program style SVP drifters per deployment. The duration of the experiment will be 2 years about, and all the releases will be, they won't be exactly the same time of the month. They'll be aligned with SWOT overpasses. And be roughly consistent release spacing physically and location though. And here is the first, so we did our first release from this site just in August, early August. So I want to show you a movie of what an example. So this is 8 drifters were released in August from this region over about a week. This is sort of the kind of thing that we expect to see, something like 20 times over, and then we'll be able to get some statistics about what is going on, hopefully. So what I'm going to show is latitudes on the y-axis, longitudes on the x-axis, date is going to be plotted there, and then this is SST anomaly in color, and the absolute dynamic topography from the L4, level 4 of ESO product is contoured in black. The SWOT swaths are in magenta. So you can see the SWOT swaths. I'm not showing any SWOT data here. It's just to show you where the SWOT passes are in time here. And then you'll see the drifter tracks. They're going to show a 4-day window. So the drifters are kind of going to inch along with a little 4-day spread of time. You can see how they move around. And you can see here the tropical instability waves in blue and the dynamic height anomalies associated with that. Initially, the drifters kind of, I'm going to try that again. Initially, the drifters kind of dip into this trough between the tropical instability waves, and then one of them circles around to the west around that anticyclonic structure. Some of them kind of stall out there, and others zoom back up to the north equatorial countercurrent and start heading to the east. And so, this is one way that we'll be able to actually get some ground truth on what the ocean's actually doing from a perspective, the real ocean's actually doing from the perspective of the currents. I didn't want to go there. So I just did some preliminary analysis looking at this particular release and relating drifter speed to geostrophy. I mean, it may not be, I guess you can kind of see from that movie right away that the drifters tend to follow the absolute dynamic topography contours. And so this is just a plot here on the left showing the geostrophic speed you get from the multi-mission of ESO and the drifter speed. These crosses, the blue crosses are kind of bin standard deviations every 0.2 meter per second. So you can see that geostrophy does explain a lot of what is going on in terms of the drifter speed, but also on the flip side of that is that there's a whole heck of a lot of scatter. There's a whole heck of a lot of other things going on. This is just an illustration of that in a time series on the right, where you have date on the x-axis for 28 days, and then on the it's a little less than 28 days in this particular case. And then on the y-axis is the drifter speed in meter per second from 0 to 1, and the solid line is the actual hourly speeds, and the dashed line here is the geostrophic estimate at the drifter location. That's giving you a similar kind of perspective to the left, but just with the one drifter. So I just started looking at frequency spectra of the drifters to get a sense of the sort of shorter timescale variability. This is all the spectra from the 8 drifters over that. This is actually an 18-day period window when they're all measuring. And, you know, you see some indication of semi-diurnal variability peak there. This is the -2 line in reference. Yeah, so more to do to look at this, but there's just some initial perspectives on what we can learn from this. I think there's a lot we're going to have to do to try to make sense. And I mean, one of the first things we have to do, so I'm going to switch to discussion of SWOT here, is to try to use the SSH from SWOT to advance understanding of the relationship between sea surface height and currents. We have many matchups anticipated. Here we just have, I mean, I think with this batch alone, there's something like 10 or maybe something like 10 so far. I'm going to just show you a couple kind of to see, give you a sense of what we're going to be looking at. And it's going to be a challenge, but here we have to deal with it. So now this is a similar movie, but it's just showing now dynamic height, absolute dynamic topography in color. And the SWOT observations are the sea surface height anomaly from SWOT plus the height crossover correction, which is not added, and then added the mean dynamic topography so that we get something analogous to the AVISO L4 observation. So inside the SWOT swaths, you have the SWOT observations. Outside, you have the AVISO. The black contours are the sea surface temperature anomaly, just for reference. But color is all now dynamic topography, and the color inside the SWOT swaths is SWOT observations. And I guess the first thing is you can see that the SWOT and dynamic topography kind of align, but you can see there's lots of interesting small scale structure and sea surface height in the SWOT data that's not present in the large scale VISO. I'll play it one more time. I mean, if you watch it a bunch of times, you might start to convince yourself that there's some correspondence between SST structure and SSH, but it's not super obvious. Okay. Okay, so now I'm just going to look at basically here. Let's see if I can get this. So I'm going to look at just a couple of matchups. So one of the things we did is, which is kind of cool, is we predicted the Lagrangian tracks to match this exact pass with the first release, and then another pass there. So I'm just going to look at those two, even though because we planned those matchups, so to speak. And then you can see there's additional matchups like here later on. I'm not going to show you those. I've looked at them. There's lots to learn from considering lots of these, and hopefully over the next couple of years, we'll have many of these, as many of these as we can handle. Perhaps more than we can handle, but just to show you two as a kind of close look of what we're looking at. So here's the actual sea surface height from SWOT, SSHA Karen 2 plus the crossover correction plus the mean dynamic topography, which is large scale, so it's not affecting too much going on here. And then the contours are from the AVISO again. The drifter tracks are in black. The arrows are showing the direction of the drifter tracks. So this is the actual data, basically straight out. And what I want to highlight right away is that there's a lot of very small scale structure, latitudes, y-axis, longitudes, x-axis. It's just a couple degrees on each side. So it's a couple 100 kilometers total spacing, total size here. But there's lots of small scale structure, something like 5-10 kilometer scale structure that you can see in here. If you look at the drifter tracks kind of zooming along here, there's not a whole lot of indication that they're responding to this super small structure. There's some perhaps, but It's not totally clear. I just wanted to point that out right away. So you see there's all this interesting structure. There's also the larger scale structures, the sort of 50-kilometer scale structure that's not present in the dynamic topography from a VISO. But, of course, there is some larger scale consistency between the VISO and SWOT to some degree. Okay, so this is what happens if I'm not going to go into details of what I'm doing exactly with smoothing, but I'm smoothing to something like 40 kilometers. I think an important question is, what sort of smoothing do you want to do? What scales do you want to smooth to try to think about currents? The smallest scale, certainly in the equatorial regions, are probably not related to geostrophic currents or balanced currents in any sense. Maybe they're related to unbalanced currents, though, but what sort of smoothing you want to do to understand currents is a question. There's some smoothing to something like 40 kilometers. Again, if you look at these plots, it's not clear that the drifters, these are 2-day drifter tracks, are following the small scale structure, this 40-kilometer scale structure and up from SWOT, right? If you look at the Aviso, it's there's quite a good correspondence, but not perfect with where the tracks are going and where the height contours are. But anyway, I'm going to go to the next thing, which is sea surface temperature anomaly. So what's kind of cool here is that in these particular cases, if you flip back and forth, you can see, so on the right side, I'm just flipping between sea surface temperature anomaly and sea surface height. So you see there's quite a good correspondence there between the sea surface height anomalies at these scales and the sea surface temperature anomalies, despite the fact that the drifters dragged at 15 meters are not following necessarily those, the contour lines there. And let's just flip to the other one. So similar, it's not perfect, but there's, again, a pretty strong correspondence between structures in sea surface temperature anomaly and sea surface height. Okay, so one of the things we can do with SWOT is we can also look at wind speed. This is wind speed. So that might help us understand the ageostrophic currents. I haven't looked at this too much yet, but just to give you a sense of what we can look at, wind speed is there and vectors from the model. And I think the point here is that SWOT observes the general magnitude of SSH gradients and geostrophic speed, but the small scale structure is also sometimes correlated with other variables such as sea surface temperature anomalies. But there's a lot that remains to be understood about what's going on here dynamically. Oh, okay. So I did calculate geostrophic velocities using the SWOT observations to get this to look. If I calculated it even on this level of smoothing here, it produced some results that just didn't seem reasonable compared to the drifters. So I smoothed even more aggressively to something like 60-kilometer scale. There's almost just eliminating the swaths, reducing the swaths to a point. And you can, just so you can see what how the geostrophic speeds in color from SWOT on the inside of the magenta lines, Aviso on the outside, and the actual drifter trajectory speeds look in color there. So you see there's some correspondence at this kind of level of smoothing. I mean, it's impressive to some degree. The Aviso, right, is something like a 10-day, it's in this interpolation of multiple altimeters that smooths in time. This is really just a snapshot from SWOT. So in some ways, it's impressive that they're even corresponding. How can we, I guess the question is, how can we do better? How can we understand more about the structure of the surface currents in the observations from SWOT that we can't get from Aviso? What smoothing is ideal? What scales are resolvable? So on and so forth. And I just want to emphasize, things we know about this. We know there's a couple complicating factors. One is geostrophy is expected to be relevant, like I'm showing, but it's not the whole story, clearly. And this is just from the model. This is at daily time mean, 5-kilometer resolution, no tides. And it's looking at the correlation between actual surface vertical vorticity and geostrophic vertical vorticity. And you can see that the blue line is showing that there's R squared, something like above a half to something like 4 degrees latitude and longitude. So it's significant. There's significant geostrophy is playing a significant role, even at these sort of fairly small scales, something like 10, 20, 30 kilometer scales, at that point, but it's certainly not everything, right? And, even kind of at daily means and with no tide simulation. The other complicating factor is that unbalanced motions contribute to the sea surface height anomaly at similar scales. So internal tides, internal waves. And I think one of the nice results that I've seen from analysis of this region is that if you look at a period of time like Boreal Spring, when SWAT had its daily repeat orbit in the April to July 2023, you can see quite a good correspondence between the LLC 4320 high resolution global MIT GCM simulation and the SWAT observations in terms of power spectra. Whether they're really simulating the same thing, power spectra is a very reduced metric, but it's nice to see that they have similar, qualitatively similar features. So this is a little bit further to the east, and it's just showing kind of characteristics of sea surface height anomaly along a swath, 10 south to 10 north. And this is the LLC 4320 on the right, the model. It's a little more wavy. You see these wave-like structures, a little more cresty in the waves. It's perhaps not so as apparent in SWAT, but actually, if you look carefully, you do see these kind of wave-like structures with 125 kilometer scale, which is roughly the wavelength you expect for a mode 1 semi-diurnal tide. If you look at a power spectrum of all the sort of roughly 100-day of passes in the springtime there of 2023, you see this nice spectral peak in both the observations on the top and the model on the bottom at this 125 kilometer scale, which is consistent with the semi-diurnal internal tide. You can actually, there's aliasing, right? Of course, if you have daily snapshots, but actually, if you look below the equator, you can see the sort of phase propagation exactly as you expect with the alias of the semi-diurnal tide on a 24-hour snapshot. So you can really actually quite convincingly show that this looks like semi-diurnal internal tide. And then you can look at sort of the spectrum at smaller scales at that time. And indeed, you see some consistency between the model and the observations. In fact, the model has more variance than the observations from SWAT out, at this 30 kilometer scale. The model is deficient at larger scales. There's less variance I tend to see in the model than the observations at somewhat larger scales than that. So that, I think, relates to the comment at the beginning about deficiency of the model representing currents in the region, is there's actually these issues at larger scales. Okay. So that's a whirlwind of SWAT. And I just want to conclude with some discussion of models, which is kind of why study some mesoscales around it's kind of addressing the question, why study some mesoscales around the cold tongue in the first place? And it's a slightly different, I think, perspective. So I just wanted to share a little bit about this. I'm going to try to talk more about this at AGU. But the hypothesis is that the submesoscale and mesoscale processes are participating in the meridionally asymmetric mean upwelling. So a number of high-resolution models, this is the mean upwelling from this 5-kilometer regional MIT GCM simulation we did, average zonally from 168 to 97 west, I believe. And there's this asymmetry where you have, well, of course, you have strong upwelling on the equator associated with the Ekman divergence primarily. So it's mostly due to this dVdy, even though you have the sloping undercurrent. And a conspicuous feature is the fact that there's this tongue of enhanced upwelling north of the equator that you don't really see to the south. So there's this asymmetry. And this asymmetry tends to exhibit itself only in high resolution eddy resolving models, not your sort of typical 1-degree resolution and coarser climate model. So it suggests eddy processes relevant to that. I'm going to try to understand. So question is, it's a scale interaction problem. How are these small scales potentially impacting the mean upwelling, the equatorial Pacific, with its consequences for, SST dynamics and climate variability? And I just want to take a little through the argument. The climatological meridional Ekman transport divergence is nearly symmetric on both sides of the equator in the Riesian and Shelton climatology. And I'm showing this, it's a little bit strange. So this is degrees from the equator on the x-axis from 0.5 to 3.5. And I have in blue is the northward transport, northward Ekman transport here. The red dash up here is the southward transport. So there's a little asymmetry in the total transport, but the I just offset this down to show that the gradients in this quantity, the divergence, are almost identical, right? So the divergence, the gradient in this quantity, which doesn't care about the absolute magnitude of it, is almost exactly symmetric, this region. So that can't really explain that meridional symmetry, because this isn't caused by the winds, is the point. And so if you, in fact, so what I'm going to do now is I'm going to use an Elias and Sawyer equation diagnostic approach to try to understand and separate the mechanisms driving this upwelling. And in fact, if you take, your mean conditions of the equatorial Pacific, density in black, and the velocities, and you plug them into kind of an Elias and Sawyer or omega. It's analogous to the omega equation if you're familiar with that. And put in your right-hand side driving as a friction associated with the wind in the upper ocean, you get a fairly symmetric upwelling response. And this is just diagnostically calculated using kind of an AX equals B solution here based on the mean state and the forcing from the MIT GCM in winds. And that's the pattern you get. This is the upwelling associated with dV dy only, so not the du dx part associated with the sloping undercurrent. So it extends a little deeper and it's a little different structure, but this is what the MIT GCM analog is. So if you flip back and forth between those two, you can see the asymmetry in the MIT GCM is not well represented by that Ekman, which is much more centered on the equator. Now, what I can do to examine the eddy effects is pack the eddy momentum fluxes into this right-hand side frictional tendency term, treating the eddy momentum fluxes as a tendency in zonal momentum. It's analogous to wind. You can do the same thing with buoyancy, diabatic effects, treating the eddy buoyancy fluxes in here. And this, just some physical intuition, this is essentially a destruction of thermal wind balance. This is a tendency associated with eddies and friction and diabatic effects to destroy thermal wind balance. So if they evolve in such a way that they maintain thermal balance, they're aligned, then you don't generate a secondary circulation. But if they evolve in such a way that they're disrupting thermal wind balance, then there's a secondary circulation that should act to restore the thermal wind balance of the basic state, which turns out to be quite good if you look at a long time mean like this. So that's intuitively what we think. And indeed, when you add the eddy effects, and it's mostly a momentum issue, you get this asymmetric structure with this off-equatorial peak and upwelling, much different from the Ekman only picture here. And if we flip back and forth now, you can see there's a much better consistency in the upper ocean between the MIT GCM upwelling associated with meridional divergence and the upwelling diagnosed by the Elias and Sawyer equation. So the suggestion here, which is quite implicit and high level at this point, speculative maybe, is that the eddies are playing a pretty critical role in setting the structure of the mean upwelling. And so that's a different view on the role of eddies in this environment I wanted to share. So lots of preliminary stuff. There's lots of work to do to understand this. I'm looking for collaborators, postdocs, interns, so on. Thanks for listening.
Thank you so much, Dan. We've got plenty of time for questions. If you could please just raise your hand.
I can't see any questions if I leave my screen open. So are you gonna coordinate that?
Fine, I'll read them to you, or
okay.
People can speak up too. Sarah has a question.
Yeah, just a really quick question. I wondered, in looking at the drifter data, are you doing anything to remove tidal motions or inertial motions from it? And I think you implied you were not, but.
No, not yet. No.
So the similarities you're seeing are even with the contamination of tides and inertial motions.
That's right. Yes.
That's nice. Cool. Thank you.
All
So there are a
right.
bunch of other questions.
Yeah. Yolanda?
Yeah, thanks, Dan. Nice talk. I wondered about if you know people looking at the near surface atmosphere and the SWOT data, and also these sub-mesoscale features and the SSTs you're seeing, and if there's an effort in this community to look at that.
I guess, yeah, I don't have a good immediate answer to that. I mean, I think the answer is yes, but I can't point you to like the right people off the top of my head.
Okay.
Maybe Bia actually could could tell you more. She's more focused on kind of the air-sea interaction, surface waves, flux side of things with SWOT in terms of there's not a lot of equatorial focus though, so in general with SWOT. So at least the SWOT science team. So Bia, do you have a thought on who is looking at kind of like air-sea flux issues at some mesoscale fronts on the SWOT community?
I know that Doug Vandermark and Justin Stopa are doing some fantastic work looking at small scale Earth interactions with a focus on clouds and atmospheric boundary layer, looking at the sigma naught observations. But again, everyone is just starting to look at this data, so I don't think we have much at this point.
Thank you. Nice talk.
Megan.
Yeah, great talk, Dan. I was really struck by that slide where you were talking about the fronts in the semi-diurnal tide. And could you actually go back to that? And I was wondering if you could just, yeah, that one. Talk us through this just a little bit more. What is the wavelength? And so, and why is it so sharp? You know, what does this look like if we're in an uncrewed surface vehicle?
Yes.
And I mean, are we seeing, you know, these sharp V's, you know, meridional velocities, or yeah, just describe it a little more.
Yeah, I'll try. Yeah, it's so what I think this is I think this particular pass, I wish I had a map, it's kind of a zoomed out picture of the kind of beams of internal tides that you see and the estimates of that from existing altimetry and whatnot. But I think this particular pass is roughly aligned with an internal tide beam that's coming up. Forget the exact. It's coming up from the South Pacific somewhere and propagating kind of towards the equator. And this is just where it happens to kind of be particularly strong, coming from south to north across the equator. It seems like it's aligned in such a way that the crests, right, are almost perfectly aligned with the swaths, right? So that the energy propagation is almost perfectly parallel to the swath to the north, right? And I guess that's the larger scale context of how I think about this. And yeah, I don't know. I don't think the model is realistic, and it's the model on the right. It's representation of these sharp crests. You don't really see that in the observations. It's nice because there's daily observations. So if you actually look at movies in some way of the SSH from SWOT or Hofmahler diagrams, you can really see. It's maybe you look over here and you can say, okay, there's some indication of these, 125 kilometer spacing features in this particular example. But if you look at, it's really almost better in a Hofmahler movie because you can actually see, it's what is it? It's like 25 hours would be two cycles of a semi-diurnal tide, and the 24 hours is the spacing between observations. So you can see that aliasing of the phase propagation actually in Hofmahler diagram. So it's really quite convincing that that's what's going on here and particularly in the southern hemisphere. And yeah, I mean, yeah, so that's what I think these things mostly are. Of course, there's other, it's, you know, you see the spectral peak in the power spectrum of a long track. I'll tell you a little bit about what the processing is. So in order to get these results, you have to remove the large scale SSH structure. And the way I'm doing that is the model and observations are treated independently, but basically you just remove a high order polynomial in the long track direction in both cases. And that gets rid of a lot of things that, you know, to isolate this signal, but it's convenient, right? That some of the correction issues, some of the other factors are all large scale. So it removes those nicely in the same way, but it also allows for those things to be different in the model and the observations. But otherwise, I mean, this is not, I just to say in the observations, typically you correct for sort of stationary internal tides. Things like that have been added back so that the observations don't have corrections to remove stationary semi-internal tide. So in that sense, they're similar. Yeah, it's kind of hard for me to go through it all here. Yeah, hopefully that's helpful. What it looks like, I think if you were measuring, say, velocity, you would see the kind of characteristic velocity of a mode 1 internal tide, however big that is, and you could figure out what the amplitudes would be based on these height anomalies. It's a pretty robust signal in the springtime. Now, in the springtime, though, I don't expect to see that sub-mesoscale vorticity because it's very seasonal, like with the tropical, it's kind of aligned with the tropical instability waves. So whether you would, what you would see in the boreal autumn now is not so clear. I'm just assuming that this sort of semi-diurnal internal tide structure would be fairly consistent year round. But so I'm treating the spring as kind of a control period where we have low balanced variance to try to understand it. I don't know. That's a bunch of rambling, Megan. I hope that was helpful. I don't know what you would see in a really, you have to look, I guess.
But you expect these to be stationary and not propagating, huh?
No, that's not so clear to me. It's not clear to me that these are like phase locked, meaning when I say stationary, like phase locked, so that the crests, you know, are exactly aligned with the same period of the tide. I mean, the phase will be shifted, right? But I'm not convinced that these are phase locked. They may be kind of what the internal tide community, they call them like incoherent or something that's not phase locked. Like, so it could be modulated with refraction a little bit between one path and next. Yeah, I do not think this is mostly phase locked, but some of it probably is in the Southern Hemisphere. You can see, actually, one of the things that's interesting is that you can see, and this was some discussion with Martin Bausman about showing this, is that you can see that as you move across the equator, the spectra on the right, there's spectra from 12 south to 0, 6 south to 6 north, and 0 to 12 north, that actually the amplitude reduces quite a bit in that kind of that wavelength as you go across the equator. And whether that's because the beam is just not quite aligned with the pass, north of the equator, or because the, waves transfer energy to other scales or what is unclear, but that's, wow. You do see that.
That's crazy. Thanks.
Shane?
Hey, Dan. Thank you very much for your presentation. I'm very, very excited about your project. That's so cool. So just a comment about what we are talking about here. So in one of the models that Brian Arbeck and I, wrote a paper in 2022 about it, when we looked at the energy in the semi-diurnal band, like the equator is really the region in the world ocean where you have some dramatic modulation of the semi-diurnal tidal energy from the large scale equatorial currents, right? So to add to the discussion you just had about with Megan here, those, tide beams that you're seeing are for sure going to be modulated very much by, your tropical instabilities, I think, or just like the large scale currents. So it's really like a mix of like coherent and incoherent tide, or phase locked or non-phase locked, I think. So for the phase locked part also, Ed Zaron and I, we just released a new model of bioclinic tide phase lock estimate that could be useful to remove some the drifted velocities And then, in addition, you can use TPX or whatever, as to remove the barotropic component. But I think you're going to have a lot of left out, semi-diurnal tidal baroclinic variability that cannot be predicted with like phase lock models for sure. So you're going to have a lot of that. And then
I agree. Yeah, everything you're saying, I agree with. Yeah.
Yeah. And then the question that I had for you is like in that exercise of like comparing SWOT, SSH derived velocity and drifter velocities, you can optimize both, right? You can optimize your derivation from SWOT, or you can optimize your derivation of velocity of the drifters. So my question is that, do you have like some capability? Do you have like higher temporal resolution than typical GDP drifters here, or do you have just hourly positions?
That's an interesting question. So I've decided to go with hourly for the most part. I don't know. Yeah, I guess so. I'm a little unclear. Can you just say again before I get into this, what did you mean by you can optimize for SWOT or you can optimize for the drifters? I'm a little unclear what you mean exactly.
I mean, it's not straightforward to calculate drifter velocities based on positions, right? You can do it many different ways, right? You can do a simple, center difference, forward difference. Right now, the Global Drifter Program hourly product used a lowest polynomial fitting into a given band of 4 observations, right? That's the method I derived in 2016, and we're like revising it to basically find an optimal smoothing function to fit to the position to get the velocities, right? But then you could try, but that model is global and maybe it needs to be adapted to, the local conditions based on the local dynamics. So I'm just saying that, in order to reduce the noise, or maybe you can optimize the velocity estimate from the drifters, the same way you're going to optimize the length scale over which you're going to derive velocity from SWOT SSH. So you can play a game.
Okay, I see.
I was just unclear in the middle.
Yeah. And I don't know I see what you mean. Now I was confused because I wasn't sure when you were saying optimize with SWOT, thought you were talking about velocities, and I was confused because it's not measuring velocity. So now I get what you're saying, because you can optimize the smoothing of the height, and then that sort of related to the velocity that you're getting. Yeah, I got it. These I think are just things that we have to work through. I don't have a good answer for you on what I think is the best thing to do. But I guess my intuition is that the drifter I don't know what, my intuition is that probably the issues are more to do with SWOT, the vagaries, if you will, than the drifters. But I mean, that would be my guess. But in terms of like whether you want to do polynomial fitting or how exactly you smooth in time, that's an issue.
Depending on the method that you use, as an example, is going to make a lot of differences on the shape of the spectrum you're showing here on the right. And so, we devised some methods to derive the velocity, the velocity from the drifters by looking also at the shape of the spectrum. So the shape of the spectrum is going to change based on the method that you're going to use to estimate the velocity of your drifters. So I'm just telling you that deriving the velocities of the drifters depend very much on the method that you choose, and it's going to affect higher order statistics such as the
isn't that going to be mostly in the high frequency part of the spectrum, right? And it's not, you wouldn't think it would affect the low frequency part, right? I mean, that's going to affect like the the semi-internal tide and higher frequency harmonics, right? I mean, if you with those processes most strongly, right? Is that the suggestion?
Well, then I don't know, which frequency range do sub-mesoscale lie in?
Well, it's not clear, but I don't know. Well, we can continue talking about this. I agree that it's a concern what you're raising, and so what the right answer is not totally clear to me. So I mean, I think there will have to be some optimization to deal with the drifter velocities, depending on what your question is. Like, I agree.
Cool.
Yeah.
All right. Ahmed has a question. Ahmed, do you want to ask your question, or do you want me to?
Sure, I'll go ahead.
Okay.
Very nice talk, Dan. Gives us lots to think about. Really enjoyed it. There's lots of interesting salinity dynamics in this region as well. Is that does that impact the SWOT signals? What's your sense for the sub-mesoscale motions that might arise from the barrier dynamics? And so the related question I had was whether 15-meter drogue drifters get too deep, and maybe that's why they are following larger scale mesoscale motions, because perhaps some of the sub-mesoscale dynamics you're talking about is more near surface trapped. I keep thinking about your averaging scale and why you need to get to 60-kilometer scales rather than shorter scales.
I mean, everything you're saying is things that I've thought about already. So it seems totally spot on to be concerned about those issues. I'm not sure what the answer is. I do know, I mean, you can see from the models, like in these, you know, that picture I showed, like this picture with the vorticity, salinity is maybe, I mean, just qualitatively the dominant factor in the density fronts north of the cold tongue here, which is not so obvious, and it's not even clear to me that that's correct. That's horizontal, and just qualitatively in some of these models, it looks like that's the case. I don't have a good, there are a couple papers that have been done about the dynamics here and models. I'm not sure. I don't feel like I understand the dynamics of these motions. It's not clear to me, for example, that they are deriving their energy from APE release, like conventional
Right.
a mesoscale motion. There may be different energetics. So yeah, in barrier layers, yes, I think, you know, if you look at the model, right, you look at the mixed layer depth, there are shallow mixed layer depths, and whether 15 meters is getting you, it may be too deep to observe. And I mean, I don't know. One could quantify that better, and whether or not we trust the models is another question. But yeah, I mean, your points are all spot on. I think those are all concerns that we have to deal with.
Right. I was just thinking of some similarities between what we have observed in the northern Bay of Bengal, which tends to have very strong contribution of salinity dynamics, albeit at much higher latitudes. It's more like 15, 18 north. And also some of the things that were done in spurs too, regarding, you know, the impact of salinity dynamics, and that was perhaps closer to your region. I'm just wondering if some of that is explained by the salinity. I'm not sure. Would it be worth looking at?
Yeah, thanks. Yeah, I mean, it's worth looking at, I think, for sure. Certainly, I mean, it's certainly easy to do in the model, right? In the model, we can work on that issue, and I've done some, but it's not developed any more than this.
I mean, just eyeballing sort of IMERG data in this region, there are lots of you know, rain bands propagating through this you know, these kind of latitudes, and I'm wondering if you know, if that plays a role, or if the high resolution models you've worked with already include the pressure forcing as well as the salinity dynamics at a scale that would resolve. I mean, it seems to resolve some of it, certainly, because I see the shallow mixed layers here.
This model is forced by JRA 55DO, so there is some, you know, to whatever degree a half-degree reanalysis in the atmosphere gets you precipitation variability, which is not ideal, but it's not, I mean, it has some of it, right? I mean, the precipitation distribution is, you know, incredibly difficult to represent in that sort of environment, but, you know, the reanalysis like that. But I mean, I think it doesn't, you know, it has some of that representation. Yeah, you know, it's not just like a climatology or something like that, a precipitation that's going into this model. So I think we can look at it here. Yeah, the other context is to maybe look at the high resolution, like the global GEOS Echo high resolution coupled model, which may be maybe a 6-kilometer atmosphere free running with an ocean at 4 kilometers could give you some insight into, I don't know how realistic, that's a question though, how realistic the process of the precipitation variability is in that model, but I don't know, just an idea.
Great. Thanks, Jen.
All right, so Megan, and then I also have a quick question.
Okay, following up on Amit's question, I mean, do we believe that these tropical instability waves affect the rainfall? You know, is there actually a tropical instability wave patterns in rainfall? And I mean, we know there is in winds and wind convergence, and so, but you know, I was actually just looking at this, and I couldn't, I didn't figure that out whether there is. But if there is, then seems like we really have to have a coupled model to look at these effects of salinity on these fronts.
Yeah,
Anyway.
that's a good point, Megan. I mean, maybe that may be the high resolution model. I just don't know how realistic. It's a new experiment. Maybe that model I mentioned would be helpful for looking at those issues. Certainly, you could look at it just from a modeling perspective. It'd be interesting to look at that from a new angle. So I mean, I don't know. This is maybe just a comment on this. I have looked a little bit at the relationships between TIVs and atmospheric properties and reanalysis in the MERIT-2, and you do see, and I mean, this has been documented more locally before, but you do see consistent perturbations of atmospheric boundary layer height, upwelling. I looked for precipitation correspondence. Didn't see, it's not super obvious, at least from my preliminary efforts. This is nothing published, but I did actually try to look for that. I don't know what, and I felt, I mean, there's some work, but I felt like it's not, maybe you're feeling the same thing, that that's not like an adequately addressed question about the precipitation variability. There's a signal. I don't know. Seems like a good question though.
Likely clouds signal, but yeah, I don't know about rainfall. Anyway, interesting.
Right. We're almost running out of time. Just to wrap up, then I want to ask you a very impartial question. You showed a couple of things where, like, the fact that you're using SWAT to compute velocity, it's bringing some challenges in this region. Could you comment on how your problem would be different if, hypothetically speaking, you had very wide swaths of total surface currents and winds simultaneously measured at this region that you're looking at?
Softball sales pitch for a science mission. Yeah. Yeah. It would, I mean, obviously it would be, I don't think SWAT can solve all our problems with surface currents here. So it's pretty clear to me. I mean, maybe there's more that can be done to learn about the surface currents. But I mean, yeah, I think the equatorial region is an obvious place where, as you go close to the equator, the height to sea surface height is not going to solve. I don't expect sea surface height to solve all my problems when it comes to surface currents. And so it would be nice to actually have direct measurements of currents at the surface here globally with spatial structure. I mean, you could imagine that would be transformative. I don't know, at least it seems to me. Sorry, I'm not the best at making it summary pitch right there, but yeah.
This is very interesting discussion. Thank you everyone for coming and engaging, and let's thank Dan one more time for such a lovely talk, and I'll see you all next week.